everybody. Get started. I was planning on streaming at 9:05, but might as well go ahead and get started at 9 o'clock. So I didn't actually promise that I was gonna stream at 9:05 or live, I guess I should say, because I wasn't really sure when I could get my daughter in to the doctor this morning, but it just so worked out that her doctor's appointment is right after this, so that works out pretty well. So I'll go ahead and get this going. So sorry about the last minute switch around. So this video is going to be the same for whether you're in the 9:30 section or if you're in the 12:20 section. Okay, so water enters a throttling valve operating at steady state at 300 kilopascals in 80 Kelvin, or degrees Celsius, I'm sorry, and exits at 70 kilopascals. And we want to know the rate of entropy produced per kilogram of steam flowing in and kilojoules per kilogram K. So and it looks like I've got a carryover unit conversion issue over here. So let's just go ahead and clearly what I meant was for this to be in SI units and not H units. Go ahead and fix that right now. So we want this not, just make this a little bit, we don't want this in kilojoules per second Kelvin. We want it in joules per kilogram K, which is what you would get if you divided that kilojoules per second Kelvin divided by kilograms per second divided by the mass flow rate. Okay, so we have this throttling process, and we know that for a throttling process, we think back to Unit 3 and the typical assumptions for a throttling process. You've got, well, it's steady state, right? Q dot's equal to 0. Don't have any power. Don't have any significant changes in potential energy. And as long as you do not have, as long as your control volume is such that the outlet is drawn not right where that constriction happens, but just a little bit further down, as long as you have your control volume like that, which we'll say that we do, the change in kinetic energy is equal to 0. And so all of those together, in addition to the fact that it's at steady state, means that it's isenthalpic. So you don't have to write down every single one of those assumptions. Say I'm assuming it's not isentropic, isenthalpic. Those are the assumptions that you would need to get there. Okay, so if that's the case, so I know H1 and H2 are equal to one another, that's great. So that's going to be enough for me to fix my state at state 2. So let's go ahead and we will apply our entropy balance, open system. And so we have the rate of change of entropy contained within the system per unit time. Yay, it looks like we got one person here. Hello, one person. So this is the rate of entropy transferred by heat transfer plus the rate of entropy transferred by mass flow into the system, the net rate of entropy transferred by mass flow into the system. So we got an inlet and an outlet to consider, plus the rate of entropy used. And we will make some assumptions. This is steady state. We also assume that Q dot is negligible. We have one inlet, one outlet at steady state, so that mass flow rate is also the same. And so I can simplify this to get sigma dot over m dot is equal to S2 minus S1. So by S1, I've got two independent intensive properties, and I'll just kind of pull note over here what my intensive properties are. We've got temperature, pressure, specific volume, quality if it's applicable, internal energy, enthalpy, and entropy. And so, when you're fixing your state, you just need to figure out which two of those that you know or that you can get a handle on. So at state one, it's pretty easy because you're given temperature and pressure. And as long as you're in a single phase, that will be good enough to fix your state. So let's go look together. So we're at 300 kilopascals, which is 3 bar, and 280 degrees Celsius. And it turns out, yes, you are actually superheated. So that's going to be enough to fix your state. Actually, let's see. So I do have that one, and this is going to be in table A4, Superheated Tables. That is going to be 7.629. Actually, while I'm at it, let's go ahead. I think I will actually go over to A4 and let's make sure that that is the number. So we may need something else. Oh, there we go. So this is at the bottom of table A4, and I've kind of zoomed in here. So this is the column for specific volume, internal energy, enthalpy, and entropy. 280. Here we go. So 7.6299. So that's perfect. And if I look over here, I can see that state 2, I know the pressure, but I don't know anything else. And so I need to figure out which two properties do I know or that I can get to. And it's pretty obvious because we already sort of went down this rabbit hole just a second ago about isenthalpic, the fact that throttling valves are modeled as isenthalpic. And so I know my H1 and my H2 are equal to one another. So I know H2 is equal to H1. And go ahead and get that H1. And you're getting that H1, of course, at T1 and P1. So I'm going to go back exactly where I was in those superheated tables. So there's my H value, 028.6. Go ahead and write that down. 0.286, and that's kilojoules per kilogram. So then this value, H2, is 3028.6 kilojoules per kilogram. And so now I just need to figure out what phase are we at state 2. And I'm sorry, oh yeah, that is 0.7. I'm sorry. I was looking at the pressure. I was like, that 0.7 or 0.07? It's 0.7 bar. All right, so let's go figure out what phase we're in. So I'm going to go to my tables here. So you can go to table A3, actually, it would be, wouldn't it? So looking at 0.7 bar, we know that that water has to have an enthalpy between H sub F and H sub G in order to be saturated, and we are slightly above that. 3068 is our enthalpy. So I know that it's superheated, so I need to go to those superheated tables. Let's go ahead and do that. Got a few more people. That's all right. So here we are. I'm zooming in just so we can see it a lot more clearly. But this is table A4. This is the column for temperature, specific volume, internal energy, enthalpy, and entropy. So we're looking at state 2. We're at 0.7 bar, and I don't like that color, but and our enthalpy is 3028. So I do need to 028.6. We do need to interpolate. See if that looks okay. So I've got 8.037. 0.037. So, and it looks like it's in between those two values, so I think I'm pretty good there. Hey. That. All right, so 8.307. I'm going to put that on my notes here. 0.7 kilojoules per kilogram K. Right. So if we plug all our numbers in, we should get 0.6738. This is going to be in kilojoules per gram K. So that's sigma dot over m dot showed by the not the conservation, by our entropy balance, that this is equal to S2 minus S1. Okay. So do you have any questions? Don't be afraid to put it in the chat. It might be a second before I see it. But if you do have any questions, just throw it in there. I'll try to keep an eye on it, okay? Right, so our next problem is an open feed water heater system. So this is a direct type of direct contact heat exchanger, and looks like we've got enough to fix our state at all of these states, right? I'm just looking at state 1 and state 2, state 3, and I've got temperature and pressure at state 1. I've got pressure and quality at state 2. I'm just gonna, just because I like to do it. So these are the things I'm looking for. Need 2 of those to fix my state, and I have 2 of them at every single one of these states, 1, 2, and 3. The only thing that I don't actually have are the mass flow rates at state 1 and state 2. So that might be something I'm going to need, but let's kind of go on. So I do need the rate of entropy production, and they want it in kilowatts per Kelvin. And you remember a kilowatt is a kilojoule per second. So kilojoules per second Kelvin, kilowatts per Kelvin, both of those are the exact same thing. All right, so they did, yeah, if we kind of look at the very last line here, we ignore stray heat losses. So you can see in my assumptions, I've got Q dot equal to 0, and then potential and kinetic energy changes can be ignored. I've got those in there, but there's actually one more that I can ignore. That's my W dot. So go ahead and throw him in there because that might come into play, but I don't know. We'll see. So since I'm asked to find sigma dot, let's go ahead and apply our entropy balance and see what that gets us. So entropy balance for an open system. And it'll be very important, I've said this before, it'll be very important to distinguish between an open and a closed system. Up until, well, pretty much all through the semester, based upon the unit that you're in, what type of system it is. But for the final exam, it would definitely be up to you to recognize, okay, I've got mass coming in and or mass going out, and so I clearly have an open system. So my entropy balance for an open system is not dE dt, it's ds dt. So the rate of entropy change contained within the system boundary is equal to rate of entropy transferred by heat transfer across the system boundary at some temperature TB. So yay, we've got I wasn't sure if anybody would turn in live since I didn't actually specify that it needed to be live. I was saying before that I wasn't really sure what time I could get my daughter in, so I didn't want to promise anything. But I'm glad to see all 5 of you. All right. So ds dt goes away. Q dot over TB goes away, so there's no heat transfer, when I say there's no heat transfer, like if I draw my boundary like that, there's no heat transfer across that imaginary dotted line. And so all I've got sigma dot. And here I do need to be careful because my mass flow rate is not the same uh, for every single inlet and outlet, right? It's not. I have one thing going out. I've got m dot 3, not H, m dot 3 S3 minus m dot 2 S2. That's going in. And we got one more inlet, m dot 1 S1. And I think actually what I'm going to do here is I'm going to put a little spot over here. So S1. So the two properties I know what? Temperature and pressure. So that should be enough to fix my state. S2, of course I know I've got the pressure and I've got the quality. So if I use the S sub F and the S sub FG, I'm not really sure if there's an S sub FG value, so I'll just put S sub F and S sub G. I look that up in table A2, I should be able to get those two things. And then of course S3 should be S sub F at 3 bar because it's a saturated liquid, right? All right, so let's go ahead and get those values. So at state 1, got 3 bar and 36 degrees Celsius. So I'm going to go look these up in my tables here. And it doesn't really matter. I could look, I'll look in table, actually, I'll look in table A2, I think. All right. Get everything in as best as I can. So this is table A2. And this is the line that I'm looking at. And yeah, that's pretty awful. So I'm actually going to zoom in on this. So this is table A3. It's a little smaller. Looking at 36 degrees. And forgive me, I'm gonna kind of cross out some stuff here just so I might be able to tell what's going on here. So it's that thick. There we go. Here's the pressure, V sub F value. Here's a V sub G value, the U value stuff, some U value stuff over there. This is an H sub F. This is an H sub FG. This is an H sub G. This is an S sub F. This is an S sub G. Okay. And that's temperature over here. All right. So at 36 degrees Celsius, we can see that in order for it to be saturated, we would have to be at 0.05947, and it's in bar. And we happen to be at a higher pressure. We're at 3 bar. So our pressure is higher than the saturation pressure. So I know that it has to be compressed. So at state 1, we're compressed because 3 bar, we're at 3 bar, our pressure is higher than the saturation pressure. And so I have an option to go to those compressed tables. And I'm actually going to show you that, but I'm going to come right back to that table A2, as you'll see in just a second. Because if I go to table A5, you'll see that the lowest pressure that I have is 25 bar, and I'm at 3 bar. So I could extrapolate, but I'm extrapolating pretty far out there. And so what I'm going to do instead is I'm going to use one of those compressed liquid approximations. So yeah, let's do that. So gotta come over here so I could see what I'm doing. So doing a compressed liquid approximation. So we're going to say our S value is approximately S sub F at whatever that temperature is. And so this guy ends up being 0.5188. And this is kilojoules per kilogram K. So we're not saying that it is saturated, we're saying it's compressed. We're making a compressed liquid approximation. So 0.5188. So 0.5188. And this was a compressed liquid approximation. Compressed S1 is approximately S sub F at that temperature, not the pressure, but the temperature. All right, next guy is pretty straightforward. So it's S sub F plus our quality times S sub G minus S sub F. This is stuff that we would find in table A3, actually. I'm sorry. Oh, did I put A3 over here? I'm so sorry. This is actually A2, and I apologize for the confusion there. So A3 is the one that's organized by pressure. So let's go to table A3, this guy over there. Yeah. So we're looking right here along this line right here. Go. And so I'm going to be making calculations based off of S sub F and then S sub G. So those are my S sub F, those are my S sub F and F sub G, and then I've got a quality of 0.92. And so when I plug those guys in, hopefully what I end up getting is going to be 6.5663. And this is going to be in kilojoules per kilogram K. Perfect. Awesome. We picked up another person. All right, so S sub F at 3 bars. So for state 3, you have a saturated liquid at 3 bars. So it's just a matter of really just using that S sub F value at 3 bar. So 1.6718. 1.68. And this is going to be kilojoules per kilogram. So if I'm kind of keeping track of what I know now I know S1, I know S2, I know S3. I was given M.3. Unfortunately, I was not given M.2 or M.1. So I can simplify just a little bit. So at this, I could apply my conservation of mass. And it's steady state, so all it's going to tell me is that the sum of the m dots coming in is equal to the sum of the m dots going out. So what's going in is m dot 1, m dot 2. I'm going to scroll down so you can actually see the picture. And that's equal to m dot 3. So it really doesn't matter. I think I do. Let's say I could write this in terms of m.1 or m.2. What I'm going to do is I'm going to replace m.1 with m.3 minus m.2. And so now I've got things a little better. It's better. So I've got sigma dot is equal to m.3 S3. We're keeping track between this guy and this guy. Minus m.2. Don't happen to know that guy, but I do happen to know S2. So still don't know that guy, but that's okay. Minus m.1, which is m.3 minus m.2. This would be S1. So I know S1, I know m.3, and so I've got one equation and really just one unknown. I need another equation to tell me about m.2. And so you were probably wondering, when are we going to apply the first law? Well, we've come to that point now. So let's do that. So we need to apply our first law for an open system. we're getting, reason that we're doing that is we're going to get m.2. Perfect. So let's go ahead and I'm going to write out the whole thing, then I'll start canceling terms out. So dE dt, rate of change of energy contained within the system, is equal to Q dot minus W dot plus sum of m dot H plus kinetic energy plus potential energy. Of course, some of this stuff is clearly going to go away, but I'm going to there for now just so I can show how things are going to cancel out. And if I look back at my assumptions, I am going to, well, it did tell me that it's steady state. So of course I know this dE dt goes away. I also know that Q dot goes away, W dot goes away, the change in kinetic energy, the change in potential energy from the inlet to the outlets, no, the inlets to the outlet, singular, is going to be 0. And so all I've got the sum of the m dot h's coming in. It's the sum of the m dot h's going out. All right, so I've got m dot 1 h1 plus m dot 2 h2 equals what's going out, m dot 3 h3. And of course, I can find h1, h2, h3, right? So h1, remember state 1, it was compressed. So I know I can use a compressed liquid approximation again. So just to kind of drive home the point, remember state, I'm going to kind of zoom in here. So this is table A2, sorry, table A2. And at state 1 at 36 degrees Celsius and 3 bar, we figured we were compressed, and we're just going to use a compressed liquid approximation. So just like that S1 was, I'm sorry, my head's in the way there. AU. This is approximately, just like S1 was approximately S sub F at T, we're going to say H1 is approximately H sub F at T. So 150.86 kilojoules per kilogram. So 0.86 joules per kilogram. H2, we had a quality, sub F plus your quality, 0.92 times your H sub FG. I believe you actually did have an H sub FG there at 3 bar, and I calculate 2552. And this is kilojoules per kilogram again, and I'm sorry, my head's in the way, I keep forgetting. And then H3, H3 is going to be, so it's, you have a saturated liquid at 3 bar, so it's going to be the H sub F at 3 bar. And I've got 560, yeah, 561.47. 560, oops, 561, 561.7. And that's kilojoules per kilogram. Perfect. So I know H1, I know H2, I know H3, I know m dot 3, and now the only thing I'm going to do is I will replace that m dot 2 with m dot 3 minus m dot 2. All right. So I've got all the H's, I've got the m dot 3. The only thing I don't know is the m dot 2, but I can certainly solve for that. So m dot 2 is it's m dot 3 times H3 H1 over H2 minus H1. And if I plug in all of those things, I end up getting 66.32. And that's kilograms per second. All right, so I think I've got everything I need. That was a lot of work to get that m dot 2, but we got it. So now we can plug in everything and get a sigma dot. I believe I've got 9.51 kilowatts per Kelvin. I will box that and be very happy about that. Perfect. Once again, if you do have questions, don't hesitate. You could throw it in the chat, and I'll try to answer it as best as I can. Glad that you're here. So probably let's see, what else do we about 20 minutes left in this lecture, so maybe we'll get to 2 problems. Try. Okay, so we've got nitrogen. It's a well-insulated diffuser operating at steady state. I've got the temperature, pressure, velocity, and the area at the inlet. And then I've got the pressure and the velocity outlet. Perfect. I'm supposed to find the exit temperature, so T2, and then I'm also supposed to find the rate of entropy production. Oh, the exit area as well, I'm sorry. Temperature, T2, area at the exit, and then our rate of entropy production. And the units that they ask for us to give it to them in is kilojoules per Kelvin per kilogram of nitrogen flowing. So that's sigma dot divided by m dot, and you can see over here to the right how I get those units. Okay, they do tell us that the nitrogen behaves as an ideal gas with constant specific heats, and they do tell us what those specific heats, what that CP at least is. If we need CV, keep in mind you can look in table A20. Show you. I don't think we need CV, but you know, you never know, so just want to at least show you or remind you at least. Now, if you needed, here's your table A20 nitrogen. Your CP was 1.039. Yeah. So, your guess as to what that CV is. Right, it's not really going to make that much of a difference. Maybe you want to go with 0.7425 or something if you needed it. Okay, and your K value is 1.4. All right, so with that being said, let's go ahead and see if we can't get T2. When a problem is asking for the temperature at the end of a process, you are more than likely going to need the first law. Maybe we need the ideal gas law. I don't know, because we do have an ideal gas. But let's see if we can get away with our first law. Yeah, because I think we might get into trouble if we try to use our ideal gas law, because I don't know anything about the specific volume or the, yeah, it's a little tricky there. So let's apply our first law. So our first law for an open system, out the whole thing, dE dt is Q dot minus W dot plus the sum of stuff coming in. So I will go ahead and write out the kinetic energy terms because I kind of know that those are not going to go away for a diffuser. Those are not something that I want to ignore. On the exam for that CP value, would you tell us which one you want us to use, or could we just use either? So I think the question is, which one of these? And I would say either one would be acceptable. If you wanted to take the properties, if you want to take it on that line, right, or the line below it, it's going to be fine with me. Good question. All right. So there's our first law. I'm going to go ahead and cancel out some of these things. So it does tell us that it's steady state. And then I know the typical assumptions for a nozzle are Q dot is equal to 0, W dot is equal to 0, you're welcome, and then changes in potential energy are equal to 0. So I am going to go ahead and cross those out. And so, of course, my M dots are going to cancel out because I've got one inlet and one outlet. And so should have H1 plus squared 1 divided by 2 is equal to H2 plus V squared 2 divided by 2. And of course, we need T2. And conveniently enough, I do have an ideal gas with constant specific heats, and so any delta H's could be approximated as CP delta T's. So I think I'm going to bring the H values to the right-hand side. So H2 minus H1 would be equal to CP T2 minus T1. So I'm just going to, I will write that down here. This is equivalent to H2 minus H1. And then on the left-hand side, I've got my velocity terms, or my kinetic energy terms, I should say. So V1 squared minus V2 squared. I'll put the 1/2 over here. There we go. Okay. And so now I can, of course, I can solve for that T2. So it's going to be what? The whole left-hand side divided by CP, and then we're going to add T1 to it. So 1, and it'll be 1 over 2 CP, won't it? So 1 over 2 times our CP, and our CP is 1.039 kilojoules per kilogram K. Perfect. And then we've got V1 squared minus V2 squared. Let's see, so V1 squared is 282 meters per second. And this is squared. Minus V2 squared, which was 130 per second, squared. And then to that entire section there, I'm going to have to add T1. So there will be a T1 over here, but I do need to make sure that the units match up. So I do need this to end up in Kelvin, so I need this whole thing to be in Kelvin. So let's go ahead and get those units correct. And then I'll add the T1 to the right-hand side. So what do we have? So 1 kilojoule is 1,000 joules. Joule is a Newton meter. It's been a while since we've done this, but okay. And a Newton is a kilogram meter per second squared. And hopefully that will get us to units of Kelvin. So, and then of course we're adding T1 to it. So we just algebraically solved for T2 and then made sure that our units were going to work out. And if I plug all of that in, I end up getting a value of 330.33. Perfect. Sorry, I'm messing with the volume. I apologize. It was just all of a sudden it was too quiet for me. I was hearing crickets. I like to hear something in the background. Okay, perfect. All right, so there's my T2, and that's part A. And then part B is, of course, the area at the outlet. So one thing, and yeah, one thing that we could do here is we could say, all right, so for part B, you may recall using this assumption of 1D flow. And so what 1D flow says is that you can define that m dot not in terms of, let's see, V dot over specific volume dA, right? So assuming 1D flow means that, um, V, that's not V dot, right? Oh, I'm sorry, area times velocity. Oh my goodness, I'm sorry. This, yeah, right? No, so that would be still apologies. There we go. All right, another cup, a little bit of coffee here. So the actual definition is the integral of velocity over the specific volume integrated with respect to area. So 1D flow, assuming 1D flow means that you are assuming that the velocity doesn't change over the cross-sectional area and neither does that specific volume. And this is an assumption you can always make in this class. And really, unless, most of the time you're going to be able to make that assumption unless you're really concerned about how velocity and specific volume change across that cross-sectional area. So we've got area times velocity over that specific volume. And it's the same at state 1 as it is at state 2 because the mass flow rate is the same at state 1 as it is at state 2. And so now we're kind of getting somewhere because I know the velocity at both states. And then of course I'm looking for the area. So let's go ahead and solve for area. So the area, it's A1 times, and I've got the ratio of the velocities. It's like we'll have enough time to maybe just finish at least this problem up, but we won't go on to the next problem, just so you have an idea of what's so this would be V2, not V1, V2 over V1. Okay, so I think I'm good there. And I do have an ideal gas, so I can actually put that specific volume in terms of the ideal gas law. So this is V over V2. Then the top part is going to be R T2 over P2. Since we only have, oh, that's really, yeah. I The only reason I'm saying, and I'm sorry, that should be 1. The only reason I'm saying no, it would have been a great idea, but I didn't actually that's 2. I'm sorry, I'm trying to talk at the same time. The only reason I'm saying no is because I didn't actually tell people that they needed to be here live. Yeah, because like I said, I didn't know when I was going to be able to get my daughter in, but awesome on you. You've made me feel good by being here on time. So it's better than just like, looking into the sad camera lens and knowing no one is on the other side. So, all right, so let's go ahead and cancel this guy out. And I know the temperatures, I know the pressures, I know the velocities. I think I'm good. Yeah, because I saw for T2 on the last one. And so if I just plug things in, I get an area of 8.357 times 10 to the negative 3 meters squared. I tell you what, how about this? How about this? I'm going to finish up. I'm going to finish up the problem, and then I'm going to take, actually, I'm going to do it right now. You're going to have to just like hold off. Just hold on for just like a hot second. Just a hot second. So, let's see. I'm going to get a Google form together. I was going to say, just email me. And I thought, well, that's going to be just a ridiculous headache. So, excellent. So spread the word to all of your friends that they should tell me that they watched the video sometime today. So, attended lecture today, sometime today, 4/8/2022. Yes, or no. I mean, this is so silly. Yes. Let's see. What is your name? Short answer. Perfect. Required. And I think that's good. Copy. All right, here we go. Y'all tell me if you could get to that. So I'm also going to put this in the description down here. I will give you extra, let's go 3 points, because I think I was a little bit, probably just a tiny bit too generous last time. Because really, I just bumped you up an entire letter grade on test 6. Okay. Okay, good. All right. So if you're watching this sometime today on April 8th, 2022, click on that form and put in your name, and I will give you an extra 3 points on your test. So here we go. Okay. And I'll add it just as an extra credit column. Okay, so it'll just be, it won't matter what test it's added to mathematically. It'll just pretend it's added to the test that you want it added to. It'll work out that way. Okie dokie. There we go. There's something. Got you something. All right, very last thing we're supposed to do is find the rate of entropy produced, and we want the units to be sigma dot over m dot. We want the units to be kilojoules per kilogram K. And so we're going to apply our entropy balance. See, it never hurts to ask, does it? Never hurts to ask. All right, so I've got ds dt equals q dot. Nope, I'm sorry, I was on a tangent there. So the rate of entropy transferred by heat transfer plus the rate of entropy transferred across the system boundary by mass flow plus the rate of entropy produced. Of course, I'm glad that you guys are here. All right, so dsdt goes away. One of the assumptions that we make about nozzles is that they are adiabatic. And so all I've got sigma dot is equal to m dot times S2 minus S1. So I've got this ideal gas, and we have a very specific way of defining the change in entropy for an ideal gas. Remember, we have, let's see, couple of ways of defining entropy changes. So if we don't assume specific heats are constant and we have an ideal gas, we're going to use that equation I just underlined. But if we do assume specific heats are constant and we have an ideal gas, we have 2 ways that we can express that delta S. I think I'm going to use the top one because I just happen to know the pressure ratio across that. I think I said a nozzle before. It's a diffuser, across that diffuser. So go. So this would be m dot times, and it's Cp natural log T2 over T1. We already solved for that T2 minus R, which is R bar over the molar mass for nitrogen, and of course this is 28.01 kilograms per kilomole or your molar mass, natural log of P2 over P1. Okay, and I think I have every single thing that I need, but I just noticed that I don't actually have this M dot. But that's okay. If you look up at part B, I actually already defined it. Um, so M dot is equal to, we'll go with the properties at state one. It really doesn't matter. A1, V1, I know both of those things, divided by the specific volume, which is R T1 over P1. Of course, this whole quantity right here is the specific gas constant, so you can calculate that. You know T1, you know P1. Just watch your units. I'm just, instead of writing everything out, I'm just going to give it to you because that doctor's appointment is right after this class. I want to make sure I get there on time. Kilograms per second. Okay. So I guess that's it. We know everything. We're all good to go. And so when I plug in all of those things, I get 0.01132, and that's kilowatts per Kelvin. So I will box that, and then we're good. We are all done. So I'm actually going to zoom out just a little bit in case you missed something. But there you go. Right. Well, thank you so much for those of you guys who tuned in. I do appreciate it. It's a lot better when somebody else is there, and you know somebody else is there. So you guys have a wonderful day. Thank you for being flexible today. And I will see you guys next week, next Monday, okay? All right, y'all have a great weekend, all right? Thank you.